Swayam Prabha. Digital India. Educated India.
Hello, welcome to lecture 10. So in this lecture, we'll be covering the biasing of RF amplifier circuits. So in the previous lecture, we had discussed about amplifier gain, how to select the input and output impedances, gamma S and gamma L to obtain a required value of gain. In this lecture, we'll be covering the other important aspect of amplifier design, which is biasing. Because see, for example, as I said earlier also, the S parameters that are given for a particular transistor configuration are for a particular biasing condition. They are not universal. So under these circumstances, then depending on how you arrange your bias network, uh, the amplifier performance can change, your S parameters can change, then also the efficiency of the amplifier can change. So what are the functions of the bias network? So first function is so these are the primary purposes of a DC bias network. So first is to select the operating point of the transistor. So we all know from basic electronics that the operating point of the transistor is an important parameter, because to select what the current, drain current that will be flowing into the transistor, or in the case of BJTs, the collector current, to set that and at the required voltage. So usually you have these ID versus VG or ID versus VDS curves. So these are the curves that you use to set what will be the current and what will be the voltage, the DC quiescent voltage. And to do that, you need to set the operating point. And these bias networks is the tool by which we set the operating point. Then the second important function of the bias network is to set the operating point of the transistor even in the presence of temperature variation. So as you must be knowing, the characteristics of a transistor change when the temperature varies. To prevent that, the bias network can be used to correct for the temperature variation. And one other important role of bias network is separation of RF and DC signals. So at the output of a transistor, you get a mixture of both the RF and DC signals. But you might need only the RF signals. So the bias network can also do that. It can separate the RF from the DC. By RF, I mean radio frequency or higher frequency. And also one other important feature or essential aspect of any bias network is power supply decoupling. So the bias network should only provide the required voltages and currents. Any variation in the power supply it should be able to decouple it from the operation of the circuit. That is, your amplifier performance should be shielded from any power supply variations or fluctuations. So these are some important role of bias network. Of course, there are two other minor aspects that the designer must also be aware, which is uh, how to ground the transistor. So grounding is an important part of the transistor setup. You have to ensure that the transistor is properly grounded. Usually the way it is grounded is, suppose you have a PCB. So suppose this is a PCB, and say you have your input network like this, and transistor is sitting like this. So these are the points which are grounded. So one way of grounding this could be, so you say you have your normal PCB board. So one way to do it is you have a via through the substrate, and then that connects to the ground. Or if you have a breadboard, then breadboard, you suppose this is a breadboard which has a grid-like structure, a simplified version of a breadboard. So in this breadboard, say your transistor is sitting here, and you can simply connect it to the ground line. So this is your ground. You simply connect. So you can create another ground line here, and say your supplies are connected to some other terminal. So in this case, this is just, it's a simple, just take your transistor terminal and insert it into one of the slots on the breadboard. So that slot corresponding to the ground line as shown. So these are some simple ways of transistor grounding. And yes, one other very important aspect, not as important as the first four, but still very important, is heat sink. So what happens is, in power amplifiers which amplify where the output power is quite large, it can cause a significant heat. A lot of heat is created by these power amplifiers. So there must be a proper way to sink the heat. So usually the most common way of heat sink design is to just use some vanes, some metallic vanes which are air cooled. So you sometimes have vanes like this. At the bottom usually, so these are like, so these are simple air cooled metallic structures which conduct away any heat produced by the transistors. Okay. Or for very high power, like say 1 kilowatt range power, where the output power is in the range of kilowatts, you need these metallic vanes, and in addition to that, for providing additional cooling, you also need water flow through these vanes. That is a separate engineering itself. These are some important factors while considering the biasing, as well as transistor grounding, as well as heat sink in amplifiers. Now, what is the schematic circuit of a ideal bias T? So So this is the schematic of an ideal bias T. What it means is that we have a very high capacitor and a very high inductor value. So if the inductance value is very high, it will allow only DC to pass. So similarly, if we have a very high capacitor value, it will allow only RF to pass through it. And so at the end, we will have RF plus DC, and this being a very high value capacitor, the DC will be blocked along this path. Similarly, this being a very high value inductor, RF will be blocked. Okay. As a result, at this end, we will get only RF plus DC. Okay. So this is what is known as a bias T. Okay. So this is, as I said, this is just a schematic diagram, and the real bias T will be, you will have actual RF components in that. So one simple way to do that is this circuit. I'll just share my slides here. Okay, so this is the circuit of an actual amplifier. So this part consists of the input matching network. Okay, this part, the left hand side, and this part consists of an output matching network. You can see two capacitors, these yellow box shaped capacitors at this end and also at this end. Okay. These prevent any DC from going out or coming in. Now these two structures that you see, this radial stub and this square patch, both have, from an RF point of view, both have very low impedance. Okay, so if an RF signal, that is microwave range signal, is introduced here, the input impedance for these square patch as well as radial patch will be very less. Now this thin strip that you can see is lambda by 4 long at the frequency of interest. Similarly, this thin strip is also lambda by 4 long with very high characteristic impedance, which is obvious from the by seeing how thin this strip is. So because this is quarter wavelength long and this is low impedance, so the input impedance seen at this point will be the inverse of the low impedance. So we'll see a very high input impedance here. So what that means is it's an RF open. So for an RF signal, it will see an open circuit here. Similarly, an RF signal will see an open circuit here. But it's a DC short because this is after all just a piece of metal. So DC can come in. Similarly, DC also can come in. And so the end result is at this point we will have a mixture of RF plus DC. And at this point also we will have a mixture of RF plus DC. But no RF will leak here. No RF will leak here. This bias network design is not just limited to passive circuits. We can also have an active version of the same bias circuit. For example, active version of the same RF of the same bias T could be, or biasing network could be, now all these circuits are given in your notes. This is the microwave transistor. Okay. These are two decoupling capacitors. So decoupling capacitors are capacitors which don't play any role in the circuit, but they are used to drain any sudden increases in voltage. Similarly, this is also a decoupling capacitor. Okay, so you have two transistors. This is the main, this Q2 is the main amplifying transistor, whereas this Q1, this is just used for biasing. Now qualitatively, so here this Q1, what it does is it sets the bias current IB2 that is flowing in Q2 and thereby sets the operating point of Q2. Now, what is the role of, so how does qualitatively how does Q1 work? So if C1 increases, okay, so C1 being, sorry, if IC2 increases, so IC2 is this current. Suppose for some reason IC2 increases, so then what happens is the voltage drop across this R3 will also increase, and so because the voltage drop across this R3 decreases, the forward bias for the emitter base, I beg your pardon, since the voltage drop across this R3 increases, the voltage at this point will be lesser if IC2 increases. If the voltage at this point is lesser, then what happens is the forward bias across this base emitter junction. So this is a PNP transistor, whereas this is an NPN transistor. So in this case, the base emitter voltage will become lesser because the base emitter forward bias voltage is lesser. So IE1, which is the current flowing into the emitter, that also decreases, and because that decreases, what will happen is IB2 will also decrease, and if IB2 decreases, then that will cause a corresponding decrease in IC2. Okay, and that's how the feedback based control mechanism works. So any increase in IC2 will be nullified ultimately because of this feedback mechanism. So if IC2 is more, again I'll just repeat the whole process. If IC2 is more, the voltage drop across this resistance increases. As a result, the voltage at this point becomes less. If the voltage at this point becomes lesser, the bias voltage across this base emitter junction or emitter base junction decreases, which in turn causes the current IB2 to decrease, because if the bias voltage across this emitter base junction is lesser, then IE1 will also become lesser, which in turn will cause IB2 to be lesser. So as a result, finally this IC2 itself, because IB2, if IB2 is lesser, then IC2 will also be correspondingly lesser, and so the increase in IC2 will be nullified by this decrease in IC2. So that's how these active bias networks work. Now we can of course have a formula for the IC2, and that is given by, so here VCC is the supply voltage. So that's I you can work this out actually. This how this formula comes. Okay, so let me continue to the next very important aspect of transistor amplifier design or biasing networks, which is the various classes of operation. So, so in the first part of lecture 10, we had discussed about what are bias networks and what are their use, how to design a simple passive bias network, and also how to design an active bias network. Now, in this part of the lecture 10, we shall discuss more about what is the use of a bias network. So, how to bias a transistor at various bias points in order to achieve various results. So, let us first consider ideal FET characteristic. So we know about field effect transistors like MOSFET. What should the characteristics of an ideal FET be? So to do that, we will simplify. This diagram is a little involved. It will take a little time. Because all these diagrams are given in a I'm taking a little time to draw the diagrams because it's important to have a correct diagram in order to explain. Okay, so first of all, this is a depletion type MOSFET or FET. So depletion type means your this cutoff voltage can be negative, as is the case here. The second thing is this is the VGS versus ID versus VGS curve, and this is the again the ID versus VDS curve. Okay, now it is necessary in this at this point it's necessary to say which is which terminal. So our FET is like this. And these are the various, so these are what are called the DC characteristics. So the by DC characteristics I mean you find these graphs by changing the appropriate DC voltage. Now in this case, for this graph only for one particular value of VDS the curve has been done, whereas for this graph for various values of VGS we have obtained the ID versus VDS. So VDS means drain to source. Okay, so these are the voltages we are plotting, and ID is this current. Okay. So now with this in mind, and of course I must also mention the various regions. So this is the triode, okay. This is the saturation, and this is the breakdown region. So in the triode region, because what is the condition that VDS is greater or equal to VGS minus VT. For a MOSFET, this is the characteristics in the triode region. This one, and VGS is greater than VT or VP, as in this case, where VP is the threshold voltage. So below, when VGS is lesser than VP, then we have cutoff or there is no conduction. Okay, so this is the condition for triode. So and for this saturation region, the condition is small correction, it should be lesser or equal to the saturation. The condition is VDS is greater than VGS minus VT. Okay. So this is for saturation, and this condition is for triode. Okay, in this region, because VDS is low, in this region value of VDS is low, so this condition is satisfied. Whereas in this in this region, once VDS crosses the limit, a certain limit, this condition is satisfied. Okay. And as we can see that in the saturation region, the current is constant. So for a particular value of VGS, we have constant current. And then after a certain value of VDS, called the breakdown voltage, the current increases rapidly. So this is like there is a breakdown in the semiconductor, and the ions, the electrons are forced out from the ions, and that's what causes this breakdown, and the current, drain current, increases rapidly. Okay, so coming back to our, so this is the beginning, of this ideal characteristics that we have drawn here. It is necessary to draw this in order to completely understand the impact of the various biasing schemes. In a real transistor, you won't find the lines so straight. So in a real transistor, there will be a little curve like this, like this. Might be like this, little curved, but here we have idealized this characteristics just so that we can understand the biasing better. Okay, now the next important parameter is what is known as conduction angle of the transistor. So conduction angle is related to the transistor. So here this is a diagram showing what various conduction angles mean. So suppose uh, my applied voltage between the gate and the source is of this nature. Let's consider first this black line, okay, this line. So here you see that the sinusoidal signal that is applied across the gate to source terminal lies above the pinch off point, okay, for all angles, for all arguments of the voltage. Okay? So for all, or in other words I can say for all phases of the voltage, the value of the input signal, the value of the voltage applied across the gate to source terminal lies above the pinch of voltage for all phases of the input voltage. Now this is what is known as class. Okay. So another way of saying is for the entire 360-degree phase of the input sinusoidal signal, the voltage, input voltage or the VGS voltage lies above this pinch off point. So what is the pinch off point? It is this point. It is this voltage, VP. So my entire input sinusoid voltage lies in this range, okay, from VP to 0. So that is what is known as class A. And class B is the case when the phase for which the phase range for which the voltage VGS remains above the pinch off point is between minus 90 to plus 90. So it's a total phase range of 180 degrees, starting from minus 90 degree to plus 90 degree. Similarly, for class AB, that is somewhere between 360 degree for class A and the 180 degree that I just mentioned for class B. Okay. And for class C, it is less than 180 degree. Okay. So once again, the range of phases for which the input voltage VGS lies above the pinch off voltage, that determines what the class of operation of the amplifier. Okay. So here is the summary. So for class A, alpha, the conduction angle is 360 degree. For class AB, the conduction angle is between 180 to 360 degree. For class B, it is exactly equal to 180 degree. And then for class C, it is lesser than 180 degree. Low noise amplifiers which are used at the front end of receivers operate in class A, and power amplifiers operate between class A to F. So now that we know what is the conduction angle, let us try to see how to design a class A amplifier. This is the circuit diagram of a class A amplifier. Now let us see how we can achieve that 360-degree conduction angle using the ideal FET characteristics that I showed a few minutes back. So I'll again switch back to my slides because this diagram is rather difficult to draw on this tablet. Okay, so I have my slides back. So once again, this is the ID versus VGS curve that I drew a few minutes back. This is the ID versus VDS curve that I drew a few minutes back. Now look, I choose my bias point here, okay, midway between 0 and VP. So my VGS is chosen, the DC bias point is chosen here. My amplitude of the sinusoidal wave is such that it lies between 0 and VP. Okay. So see, this amplitude is between 0 and VP. So now when I apply this, so this curve shows the input signal with time. I have just inverted the axis. So time is now the vertical axis, voltage is the horizontal axis. So this curve, in this curve, I apply my input voltage between this VP and 0. Now you have to understand, of course, this VP is negative. It's an, as I said, it's a depletion type transistor. So now this amplitude of the input signal covers the entire range from 0 to VP, and corresponding current that is produced is shown here. Okay. Now this is the current range, okay, that will happen for the variation of this input volt. So then now if I plot the load line, okay, so this RL is minus 1 upon RL is the slope of the load line, fine, and the way I have inputted my signal, it produces the VDS that is produced across these two terminals. You see, it also covers the entire range from the knee point, knee voltage VK to VDS max. Okay. So this way you get the full. So this way what happens is the transistor is on for the entire range of the input signal. Okay. The VGS is above VP for the entire all phases, and correspondingly VDS is also on, or VDS lies in the saturation region for the entire input signal, and so VDS simply follows the input signal like this. Okay, so now that VDS follows the input signal, it is also a sinusoid. This capacitor simply acts as a block, DC block, okay, and you have this voltage, which VDS, which is a sinusoid appearing across the load, and since the load is resistive, you have the load current also is a sinusoid. Okay. So let's again recap what happened. You have an input signal across VGS, corresponding VDS spanning the entire saturation voltage range is produced. This VDS causes an ID which is sinusoid given by this red line. Okay. Now this ID contains a DC component, IDC, which is blocked by this capacitor, and finally you simply have this dotted line appearing across the load resistor. So in a class A amplifier, what do we see? The input is a sinusoid, the output is also a sinusoid, okay, and the voltage across the drain to source terminal is also a sinusoid. Let us now see a class B and C amplifier. So for a class B and C amplifier, the circuit diagram is like this. The difference between the class A and the class B and C amplifier is that there is this additional, this green box that you see, this resonator is present. What this resonator serves, as we shall see, is to absorb any higher order currents that may be flowing across this terminal. So let us see how the biasing happens in a class B amplifier. In a class B amplifier, recall the conduction angle is 180 degree. So only half the sinusoid, only for phases for half the sinusoid, the input signal will lie above Vp as seen here. So this is my DC operating point, or my voltage, or VGS value, the DC value of VGS, which is the operating point. It is here. Okay? It doesn't lie on this line. Okay? And that is obvious, right? That DC operating point is here. And that's because, see, the DC operating value of this sinusoid, input VGS, will be along this green dotted line, and that corresponds to this DC operating point. Okay? Now, the corresponding current, DC current, is given by this IDC value. My load line RL is such that it only covers the range from the knee voltage to VD. Okay? This in turn causes the VDS to be present only for the voltage ranges of VK to VDD, okay, which corresponds to 50% duty cycle. And correspondingly, now since only 50% duty cycle for VDS is actually present and across the transistor, the current will also be for 50%. The current flowing, the drain current flowing through the transistor will also be present only for 50% as shown by this red line. But now see, this current is present for only half cycle. For the remaining half cycle, the drain current is 0, which basically means that there is significant harmonics present in the drain current. And these resonators, this green box that is added to that class A circuit, that absorbs all the unwanted harmonics and allows only the fundamental to pass through, okay, causing this green dotted sinusoid that you see to appear across the load resistance. Okay, it might not be clear. Again, I'll just go through the entire process. So first of all, I adjust so the input signal is above Vp for only half the sinusoid. Okay, it's not only the top half of the sinusoid, it is above Vp. For the bottom half of the sinusoid, it is below Vp, and so no conduction occurs. For the bottom half of the sinusoid, transistor is off. Correspondingly, I also choose my DC operating point for VDD, for VDS, I beg your pardon, such that the output at VDS also conducts only for 50%. Okay. So what I mean is, here say my DC operating point for VGS is this point. Okay. Now my current could be any value. Okay. I could have taken my current here, any point. But I choose this value because this value, okay, this red dot, which corresponds to VDD on VDS, because that also corresponds to 50% of the VDS sinusoidal duty cycle. Okay. Now, because VDS is also 50%, my current in the drain current is half sinusoid, fine, and because it is half sinusoid, there will be significant harmonics which are absorbed by this resonator, and at the output I simply have a sinusoidal current. So you see that both for the class A and class B, the output, the current at the load end is sinusoidal, and since the load itself is resistive, so the voltage across the load must also be sinusoidal. So in both class A and class B amplifiers, the input and output voltages are always sinusoidal. It is just that the drain current is not sinusoid. The drain current is on for 50% duty cycle, and that's why the efficiency is higher in a class B amplifier. Okay. Now I would like you to I would like you to do the same thing for the class C amplifier that is given here, and I would like you to show how using these biasing conditions we are obtaining less than 180-degree conduction angle. Okay, so that I leave as an exercise for you. Hello, welcome to another part of lecture 10. So in the last part we had covered the concepts of biasing of transistors for amplifier design, and there we introduced you to the various classes of amplifiers. In this lecture I will be covering one more important aspect of amplifier design, and that is noise. How to take into account the noise figure of a circuit of an amplifier. What is known as the noise figure, and say if you have to design an amplifier with a given noise figure, how do you do that? So I'll cover that, but before that I'd like to tell you, since we are part of this course, this amplifier design that we are discussing, this is a very important role to play in 5G communications. I'll just explain why. So I'll just take a few minutes covering this 5G and this amplifier design, and then I shall move on to the noise design, using design for achieving a particular noise figure. So this is something interesting. In 5G, the concepts are a little different as compared to the earlier standards. How is it different? First thing is, in 5G, OFDM modulation is present. Now, I don't want to go into the details of OFDM modulation, just to let you know that, say, OFDM modulation has somewhat a structure like this. So there is a center frequency, okay, and the problem with OFDM modulation is what is known as high PAPR, or peak to average power ratio. Further, each of these, so this is OFDM, this is an OFDM pulse. Now, the full form of OFDM is the full form is orthogonal frequency domain multiplexing. Yeah, so coming back to OFDM, the why it is called multiplexing is because actually in reality there are actually multiple such pulses present together, and each carry some information, and it's called orthogonal because the peak of any of these lobes correspond to zero value of the side lobe. So that way at the peak value there is no interference from the side lobe. So that's why that's one advantage. But then the problem with OFDM is that because of this high peak to average power ratio, that that requires a lot of that puts a lot of pressure on the power amplifier, because the power amplifier has to amplify linearly both at the average power level as well as at the peak power level, and that's quite difficult. And further, this is further complicated by the fact that the modulation schemes may be various, like you may have BPSK, QPSK, WAM. So all these modulations in turn will have their own different OFDM pulses, and each will have their own PAPRs. So your power amplifier has to be optimized. Okay. One way it is done is by what is known as load modulation. So what is load modulation? Now, while discussing the various amplifiers, the load ZL, recall, was constant. But to achieve this uniform gain, linear gain at both the peak as well as average powers, it's not so easy to do that if you have a constant load. So the ZL has to be dynamically changed. Okay, so dynamically change means while the power amplifier is operating, you have to keep changing ZL. Now that is not physically possible. You cannot, you cannot do that. Actually, you cannot remove the load and physically, mechanically remove the load and put another load. It has to be done electronically and at the high power levels. And so that is an active area of research now. And on the receiver side, you have something called MIMO. So the receiver will receive signals from multiple sources. Okay, and it can be shown that the signal that is received, we can have a statistical description of the received signal, and based on that we can have our receiver. So the receiver itself will not have just one input, it may have inputs from multiple antennas, and to process that signal and ultimately derive what the information is carried, that is another challenge that is faced in this 5G. So these are two major design challenges for 5G. One is MIMO and this high peak to average power ratio. One thing that is happening is that the power amplifier itself is becoming a part of the information transfer. Whereas in the old technologies, the power amplifier was more like a fixed entity. It was just used for amplifying the signal. But now with this 5G, what is happening is the power amplifier itself is an intelligent or part of the whole information transfer. It can, by changing its power, the amplification, the gain, that is gain or phase response of the power amplifier, we can actually modulate the information being transmitted. So just wanted to let you know let's go back to our noise. So let us start from the basics. Okay, what is noise?